Hello and welcome to the first lesson of our C Programming Foundations tutorial series. I'm Reza and I'm happy to have you join me on this journey to mastering the C programming language. Have you ever wondered why C language is a big deal in the world of programming? Let me take you through some cool reasons why learning C is super useful and exciting. First off, C is like the grandparent of many modern programming languages. It's been around since the 1970s and it's still super popular. By learning C, you're not just learning a language, you're learning the history of programming. It's like getting a behind the scenes tour of how things evolved in the tech world. Now, think of C as your gateway to the programming universe. Learning C makes it easier to pick up other languages like C++, Java, and Python. It's like learning Latin to understand English, French, and Spanish better. C gives you a strong foundation and makes learning other languages feel like a breeze. C is also known for its speed. It's like the sprinter of programming languages. This speed comes in handy when you're working on systems where response time is crucial, like in gaming or real-time systems. Another cool thing about C is that it teaches you discipline. It's like the strict teacher who insists you understand the basics really well. C doesn't do a lot of hand-holding, so you learn to write efficient and error-free code. This is a skill that'll make you a better programmer in the long run. Lastly, C is everywhere from operating systems like Windows and Linux to various applications and even in embedded systems like microwaves and car ECUs. Learning C means you get to understand how these everyday technologies work under the hood. So in a nutshell, learning C is like getting a master key to the programming world. It opens up a lot of doors, helps you understand how tech works, and makes you a sharper programmer. It's challenging, sure, but also super rewarding. Are you ready to dive into the amazing world of C? Let's get started. The IPO model, consider it the original structure of computing. This model encapsulates the fundamental flow of data and operations within a computing system. Let's break it down. The first letter stands for input. It's the starting point, the gateway through which data enters the system. This can be anything from user interactions like keyboard input or mouse clicks to data from sensors or other devices. Then comes the P for processing. This is where the real brain power comes into play. The system takes the inputs, does its computational gymnastics, crunches numbers, sorts through data, and runs all those nifty algorithms. Is where the real magic happens, where all the heavy lifting takes place. Finally, we have O for output, the grand reveal. After all that processing wizardry, the system produces results or actions. This could be anything from displaying information on a screen, creating a sound, sending a message, triggering some other form of external communication, or activating an actuator. Essentially, it's the system's way of saying, here's what I've made from all that processing. Now, when we look at the IPO model in the context of software development, it's a fundamental idea that helps developers understand and design the flow of data and operations within their systems. This concept has been around for quite a while and is a fundamental part of computer science and software engineering. It's a simple yet powerful model that underpins the functionality of virtually every software system out there. Even dating back to the early days of computing, the IPO model has been a cornerstone of how we conceptualize the flow of data and operations within a computing environment. Let's apply the IPO model to a calculator program. Input. The input for the calculator program would be the numbers and operations provided by the user. The user can enter numbers, typically through the keyboard or a graphical user interface, and select an operation to perform. Process. The process component of the calculator program would involve performing the desired mathematical operation on the input numbers. This could include addition, subtraction, multiplication, division, or more complex operations such as exponentiation or square root. The program needs to implement the necessary algorithms and logic to carry out these computations accurately. Output. The output of the calculator program would be the result of the mathematical operation performed on the input numbers. After the calculations are completed, the program should display the result to the user, typically on the screen or through a graphical user interface. Alright, let's talk about something cool. Google Translate. Now, let's see how it works, kind of like a recipe. Imagine you have something you want to translate. You type it in or say it. That's the input. That's you starting the whole thing. Next, Google Translate gets busy. It's like a chef in a kitchen, taking what you gave it and mixing it up. That's the process part. It checks the words, the grammar, and what the sentence means, then uses its super big brain of language rules to figure it out. The last part is the output, which is just a fancy way of saying the result. After Google Translate has done its chef work, it gives you what you asked for, but in the language you wanted. It could pop up on your screen, talk to you, or even give you a written note of the translation. So it's like this. You give it something, it cooks it up, and then you get what you asked for, just in a different language. It's like magic, but with computers. And guess what? A lot of the apps and programs we use do the same kind of magic trick, whether they're for talking in different languages, handling money, or playing games. It's all about that input process output thing. Kind of like a secret recipe for all the cool stuff we do on computers. Here we have some more examples of how IPO models apply to software systems. In software engineering, data structures and algorithms are often referred to as the core components or building blocks of software development. When we think about data structures, we're talking about the organization and storage of data within a software system. This data acts as the fuel that powers the IPO model. In the IPO model, the input phase is where the data enters the system, setting the stage for the subsequent processing and output. Think of data structures as the containers that hold and organize the input data, ensuring that it's ready to be processed and transformed as needed. Now, let's shift our focus to algorithms. These are the problem-solving procedures and recipes that guide the processing of data within the IPO model. When we reach the processing stage of the IPO model, algorithms step into the spotlight, taking the organized data structures and performing their computational magic to derive meaningful and valuable results. Whether it's sorting, searching, or any other data manipulation task, algorithms are the driving force in this pivotal stage. As we arrive at the output phase in the IPO model, the results of the algorithms processing are displayed, communicated, or further utilized in various ways. The integrated data structures and algorithms have worked hand in hand to transform the input data into a valuable output, showcasing the power of this model in action. So you see, data structures and algorithms lie at the very core of the IPO model, providing the tools and methodologies needed to manage, process, and extract value from the input data within software systems. Like a well-oiled machine, they ensure that the data flows seamlessly through the input process output pipeline, enabling software to perform its digital wizardry and produce meaningful outcomes. Let's look at a simple example that involves both data structures and algorithms. Data structures. In the case of a leap year finding software, the primary data structure could be quite simple, such as a single integer variable that holds the year you're checking. However, if you are working with multiple years or need to store results, you might use more complex data structures like arrays, lists, or even a custom object. Algorithm. This is the step-by-step procedure the software follows to determine whether a given year is a leap year. A year is a leap year if it is 1, divisible by 4 but not divisible by 100, or 2, divisible by 400